Okay, good. Now, so at least at this stage, you feel that that's cool. It is a qubit because it can precess, right? But how do you do a general 1 qubit gate? How do you do rapid oscillation? That's what I want to talk about. So let's look at Lamarck precession. No, I don't need to. Do I need to? Okay, no. Let me go back to the previous equation. Now we know that H equals to half E. So I forgot to put the paper, but it's the same two paper I have been talking about if you want to take a look. And obviously, my cheat sheet also missing negative E, right? And with this is equal to 1 over E sigma Z minus 1 over EJ sigma X, which we already mentioned before. This is the Hamiltonian. Before we do the sweet spot, before we do the diagonalization, whatever, right? This is the general one. We did not do anything. Now you need to trust me. If Ng of T equals to Ng0, this is the charge, right? So this is no simplification, no sweet spot yet. It means that the background charge is not a constant. We have been talking about saying that it's a constant, like, for example, equal to half or whatever, right? If this is not a constant, for example, I can change it to this form with Ng equals to eta times cosine omega 1t plus phi. So it has a phase, right? Let's say I do something so that its background charge is oscillating. But you can guess, how can I do that so that background charge is oscillating based on what we just discussed? Yeah. Oscillate. Which one oscillating? Very good. Right? I mean, what if my Vg equal to Vg0 plus, I don't know what to say, maybe let's say A cosine omega 1t, for example, yeah? Just a constant, this is the DC, think about DC bias, okay? You start at half, for example, Ng0 equal to half, and then you have 0.6, negative 4, just like what we learned in E124. Now you have the small signal on top of the DC bias, right? And let me remind you, maybe it's good to remind here what is Ng, right? Ng is to Qg divided by 2E, where Qg equal to Cg times Vg, right? So if you change the Vg, you are going to change the Ng, right? It's going to have some effect. So if I do this, and then sweet spot. Now we operate on the sweet spot, which means what? Like what you just asked. Ng0 equal to half. Right? You can think about this is DC, this is AC. Small signal on top of a DC signal. You okay with this? Any signal electrical engineer, we know this very well. We always play with this linearization of the circuit, right? So, for example, you bias a transistor common source amplifier. The gate is at 1 volt. Then I apply small signal. It fluctuates between 0.99 volts and 1.01 volt, right? But we say the signal is plus minus 10 millivolts. But it needs to fluctuate about the DC bias. And this is exactly what's happening here. We have an Ng, right? Due to this gate voltage, I have half Ng, and then you fluctuate it about half. That's all what it's saying here.
So the DC component is adjusting Ng there, and then the AC is about.
Yeah, so DC component make it equal to half. Yeah.
That's the Vg dot.
Yes.
You're adding an A cosine.
Right. So you kind of think that Vg naught give you Ng naught, and then A cosine omega 1 give you eta cosine omega 1. Yeah. But we did not go through the math of the circuit because this is not straightforward, because it's not Is it? Maybe it's straightforward, actually. Just multiply by CG divided by 2E. But we don't care about this. Just assume we can do that, okay? Now, yeah.
Is the ng the same, like ng of p equals ng0 minus ng of p? Like
Yes.
ng be the same?
Oh, I'm sorry. Yeah, this is a bad notation. Yeah. Yeah, you're right. How about let me see. How about this, right? Because I only use this one time, I just call it 2. How about this? Because I've been using lowercase for ng before, so I want to keep lowercase. How about this? Okay, so this means AC, this DC. Okay, because later I'm not going to use this ng anymore. It is the eta that is important. Again, this cosine omega t, I put the wrong bracket, it should be here. Okay, now, then what? Now, it's a sweet spot, right? Then let me rewrite the Hamiltonian equal to half E times sigma z, right? But because what is E now? Because it's at the sweet spot. I'm jumping too fast. Let me do a little bit thing. Let me continue to look at what is E, right? I also forgot. What is E? E equals to 2, right? Let me see. How do we define E? E equal to EC times 1 minus NG, 1 minus 2 NG. So E equal to EC times 1 minus 2 NG, which is equal to EC times 1 minus 2 NG0, and then plus 2 NG2 of T. Is this okay? Because I just plug in the NG equal to this, I have NG0 and NGT. Right?
First part is general.
Yeah, the first part is general, and because it is sweet spot, so this is just equal to EC times 2 NGT, right? When NG0 equal to half. When NG0 equal to half, this term is cancelled. And before that, when I don't have this small signal, the whole thing is 0. Get it? Right? So Hamiltonian is equal to negative half. Now E is just equal to 2NG2 times EC times sigma C minus half EJ sigma X, right? I just copy EJ sigma X. This is easy. How about this one? Half E, but what is E now? It's just equal to 2NGEC. Again, when I don't have this small signal, this whole term is 0, right? Then it reduces to half EJ sigma X. So with this is, and then I cancel the 2, I plug in the cosine. It becomes eta cosine omega 1t plus phi. Did I do something wrong? Oh yeah, I missed the negative here. Negative. Because I have negative here. So I need to copy. I'm just missing the negative. And then, but I want to write the NC also. I don't have enough space. Negative EC sigma Z minus 1 over 2 EJ sigma X. So these are all math. A little bit confusing, but not that important, right? You don't have to memorize. I don't expect you to be able to derive, right? But I expect you to be able to follow. The main point is what? You understand that we have a DC component and an AC component for this NG because we have a DC component and AC component for the gate voltage, VG. And we also use the sweet spot to help us simplify. And because of this, then we come up with this expression. Again, I have the sigma Z, but with a cosine. And I have sigma X with a constant. That is the new Hamiltonian. That might ring the bell, right? Did we learn about anything about the magnetic field, that you have a constant and also have a oscillation field?
A rotating wave.
Even before rotating wave, rotating vector, right? We have a B field in the z direction, and then I have a small magnetic field cosine omega 1t in the x direction. Remember that one?
That gives you
We-
the precession of
Ex-
the clouds in the X.
Exactly, that gives us the rapid oscillation, right? When I got a magnetic field. The only problem is here, this is in the z direction, this is the x direction. The constant one is in the x direction. The rotating one, the oscillating one is in the sigma x direction. But of course, doesn't matter. Who care about whether it's x or y, right? For physics, because the universe is isotropic. It's just because you're standing here, you feel that the z is this direction. But for those quarter away from this Earth, maybe in Europe, our z direction is the y direction or x direction, right? Yeah.
Well, I'm comparing this with so here, spin case omega 1, 0.
Yeah.
Here,
Don't think about that yet. If we try to map to the spin qubit, this is not exactly mapping yet. You're just saying that, okay, now I have, it's just like this. I have a constant magnetic field in the x direction. And then now I have an oscillating magnetic field in the, this is C, this is X, in the X direction. Right? This is what this Hamiltonian telling us. And of course, if you try to play with this, it's actually moving you from the plus X to the negative X, which is the maybe plus state to the minus state. But we don't want this, right? Just for the formalism. So what we are going to do is not a big deal. We just do a rotation. So we won't go to the math, but this is very straightforward or intuitive as before. What do? We transform x, sigma x to sigma c by rotating x up, right? Or rotating the coordinate, then x is pointing up, right? Then it becomes sigma c. But what will happen to sigma c when you rotate to the other side? Exactly, it becomes negative sigma x. Okay, I did not do the transformation matrix, but you do it, you should get it. I actually did not try myself. Then the Hamiltonian becomes what? Negative 1/2 EJ sigma z. Why? Because this is negative half EJ sigma x becomes sigma c, right? And then the other part is what? EC eta cosine omega 1t plus phi sigma x. Why? Because this is negative sigma c, right? So negative sigma c becomes negative sigma x, so it's plus EC eta cosine omega phi, t phi sigma x. So what do? How do you find out how it operates on a general state? Solve the Schrödinger equation, right? But we are not going to do that because, let me write one more line. Right? If I do that, then the whole class is a failure. But now if I write it as this, this one we can further transform to this. H bar omega r cosine omega 1t plus phi sigma x. When I transform this, it's very clear because EJ equals to H bar omega L. Why? Because we are working on a sweet spot. Omega L equal to E squared plus EJ squared. So now E equals 0. So of course this is equals to EJ, right? As NG0 equal to half. So E equal to 0, right? So it become a perturbation for that one. So the EJ is just H bar omega L. How about this one? This one, just a definition. I define omega r equal to EC times eta divided by h bar. So I did not do anything new. Look at this. I did not do anything new. I just substituted some constant, right? Why do I want to do this? Because then you turn back to the notes we learned in spin qubit. What do we know about the Hamiltonian of this system? We have a B0 pointing up. We have a B1 cosine omega 1t plus phi oscillating in x direction. It has a Hamiltonian equals to h bar omega L divided by 2 sigma c plus h bar omega R cosine omega 1t sigma x. And we already solved the Schrodinger equation for this guy, which is a rapid oscillation, right? Rotating about z and keep going down from North Pole to South Pole, right? They are exactly the same. But now I realize that I'm missing one minus sign, but this is not that important. I need to check it. But do you see that? So we are done. We created a single qubit gate, arbitrary single qubit gate. How do you control this single qubit gate? You need to control by using EC, eta, and EJ. EC and EJ is difficult control, but eta is okay, right? Eta is okay. So this is still not a good way. So we further do another approximation to have a deeper understanding. Is again use the rotating frame approximation. Okay, so let's copy the Hamiltonian again. We have h equal to negative h bar omega L divided by 2 sigma c plus h bar capital R, which is the rapid, no, not rapid, plus phi sigma x. Okay, so what I'm going to do is this. I just to add a sine term and then remove the sine term and then subtract a sine term. Right? So for this one, I will have sigma c. The first term is okay, right? I don't change it. The second term, I'm going to do this. R divided by 2. So what do I do? Cosine omega 1 plus t plus phi. It's difficult to see. Okay. Sigma x. I'm going to plus psi omega 1t plus phi sigma y. Are they the same as before? No, right? I need to further plus cosine omega 1t plus phi sigma x. So I have 2 cosine term and divided by 2. Then they are the same, right? But then I have one extra sign, right? What should I do? Minus sine omega 1t plus phi sigma y. And I should not have this one here. And what does it mean? This term I call it, how about I call it A plus? This term I call it A minus. Let's look at the frame. This is x, this is y. So for A plus, what does it do? It has a cosine component and a sine component, but they all go in the positive direction, right? So if I start from here, it's going to rotate in the counterclockwise. Make sense? Because you just add them, right? Cosine, this is theta. Like cosine theta plus sigma x, and then sine theta plus sigma y. Okay? How about the negative component? It's rotating in opposite direction because it's subtraction. So, okay? So, if we just stay in the A plus frame. So now it's the rotating frame approximation. Two vectors are rotating together. I stay in the A plus frame, which is rotating. Then the other is leaving me very quickly in 2 omega, like what we discussed earlier. And I'm in this frame. If you do all this math, I can ignore the A minus term because it's rotating fast. Again, this is rotating frame approximation. Then H is going to be equal to H bar omega L divided by 2 sigma Z plus H bar omega L divided by 2 cosine should I put cosine omega 1t or cosine just cosine phi?
Yeah, I guess just you're rotating at omega.
Yeah, very good. I am rotating at the same frame, right? So it's not, for me, there's no rotation. It only has the initial. Do you see what I mean? Because I'm working with this vector. This is a new frame. The merry-go-round. Now I jump on this merry-go-round. Then this merry-go-round is not rotating for me. The rest of the world is not rotating, right? And then there's another merry-go-round rotating in opposite direction that make me feel they're rotating really fast, averaging very fast. Again, I ignore that merry-go-round. Okay? So this is just this one plus H bar omega L divided by 2 cosine phi. I forgot this is sigma x and sigma y. Which is, I can further summarize this. And I make another mistake. If that is that, if it's rotating in that way, should this still be omega L when I change the rotating frame? It was rotating in the world by omega L. Now I jump on the rotating frame, then what will happen to this omega L rotation?
Omega L minus omega 1.
Omega L minus omega 1, right? So I make a mistake here. Omega L minus omega 1 divided by 2, right? And this one, I call it delta, detouning, right? That's what we learned before. And then I have this H bar omega L divided by 2 cosine phi sigma x plus sine phi sigma y. Do you recognize this equation again? Probably not, right? But we had that before the midterm. Recall the spin with rotating magnetic field. This one, we have a constant B, and then we have vector rotating. Instead of just oscillating, it's rotating on the XY plane. We did that before, remember? I still remember that class, I recall it. I did not go in person. Rotating. We have 3 types, right? We have 2 types, right? One is oscillating magnetic field in the X direction. Another is rotating magnetic field, which will do this rotating frame approximation. Yeah, we did that in the assignment also. Okay, anyway, it has the same form. Exactly the same form. Go back to check. So if there's the same form, and we prove that at that time the spin qubit can be used for arbitrary gate, arbitrary rotation on the Bloch sphere, then this can be done also. Is that okay? So here what I'm proof is that we don't have new math. Everything is the same. If you recognize that the fake magnetic field is just E0 EJ. Okay, if you recognize that, you agree that, then the math is exactly the same. And we can do any arbitrary 1-qubit gate. Now, by what? By playing with this delta, the eta. Eta is where? Eta is in omega r, embedded in omega r. Right? So you just change your gate pulse and also the phase. This is very important. Because it's phase, if this is 0, this is 1, right? And this is 0, right? Then you are rotating about the y-axis. If this is 1, then you are rotating about x-axis. If this is 1, then you're rotating about the y-axis. Now I can rotate at any axis I want. Isn't that I can build the rotating any 1-qubit gate?
What's the definition of
Phi is don't mess up with the Josephus junction. The phi here is the initial phase of the gate voltage. Yeah, so this is very important, right? You see that the control of the qubit need to be so precise. The phase of the signal come out from your keysight equipment need to be so precise, right? If your phase shifted, then you're actually not rotating about x, you're rotating a combination of x and y. Of course, I don't know this well. People must have some remedy to reduce the problem. At least now they usually, the control equipment is not a main source of noise, I think. Otherwise, they would have pushed keysight or others to improve, right? It's other source, like two-level system, whatever. Yeah, but we are relying on the phase to do quantum computing, the phase of a signal, just meaning that your sine wave, when you start going from 0, at time you're 0, whether it's 0 or whatever, okay? Now, so this is the summary, the implementation. We show that this is the Hamiltonian, I just showed you, right? You can decompose into like a spin qubit precessing about the magnetic field, but the magnetic field is not a real magnetic field. I think I have the typo. It should be EJ. Am I right? Oh, no, it's right. EJ is on X. Yeah, EJ0J, right? And this E equal to this. And all you need to do is just make U so that you have this background charge changing by this. And then you have this one. Okay, so this is just a summary. How do you do a 2-qubit gate? We don't have time, and I want to just quickly go over. For example, of course, if you are 2-qubit, you have two transmods. But remember, here I have two Josephson junction, right? Again, this is a tunable flux tunable qubit. You will pass a flux here, right, like this, perpendicular to the screen, and then your EJ is going to be a function of flux instead of constant. Okay, and because you have this EJ is changed, then what happened to its resonant frequency? Remember, EJ participates in the resonance, right? Where is that? I forgot. Here, EJ H bar omega. It participates in there, right? So you can tune it so that they have different frequency. So what it does is this, a hand waving explanation, like what you mentioned in this paper. If you're 2-qubit, you have a 0, both a 0 or both 1 that state, then you are not going to exchange energy because you're coupled by this capacitor. But if your 1 is 0, 1 is 1, then for the basis state, then you will start oscillating, right? It's just like two harmonic oscillator. You will exchange energy, okay? Then you will get something like this, a swap gate like this. And you can see this is, of course, correspond to 0, 0, 0, 1, 1, 0, 1, 1, right? And you do see that they are swapping. As the time goes by, all the energy will come here and then come here, right? So you can do something to control the swapping with this gate, and then you just do it right so that when omega s divided by, when omega s times delta t divided by 2 equals to pi over 2. Then this becomes 0. This becomes negative I. Negative I, 0, right? Yeah.
Is there a reason why called I swap and not just the swap?
Yeah, now do you see that? Because you have an I here.
Oh, okay, right.
Okay?
Right.
Because, yeah. So,
There's a station.
so this is a C0 gate. This is an entanglement gate. And in order to form a general computer, you need qubit gates and entanglement gates. Remember in the qubit, just like in assignment 3, right? Many of you wasted your time because I gave you the wrong suggestion. Maybe not all of you. I already fixed it before you do it. But 2 of you or 3 of you, right, got screwed up because I gave you the wrong suggestion. We want to implement the control NOT gate, but we start with the control phase shift gate. Remember? And then we get the control gate. Because in that case, control phase shift gates is easy to implement for a spin qubit. Now, here naturally, the Hamiltonian is easy to implement the I swap gate. So people will start with the I swap gates instead of C0 gate. Okay? So that's what I want to say, and I already consumed the whole class. Maybe next time I will just go quickly on the microwave part. Let me see, right? I will still keep to it. But I think I achieved the main goal of this class already. The rest will be just add on. Yeah, question?
I have like
13? It will, it's an approximation. So what we're saying there is that, okay, overall, because when I have some action, it already go around on me, like the magnetic field is spinning around on me already, right? So on average, it has 0 effect. But but its approximation definitely has some error due to it. The reason I have 2 is because I just playing with the math. It was 1 cosine, I just make it 2 and divided by 2, right? And then I add and minus sign, and then I say, hey, this group, I can ignore it because it is oscillating fast. Oh, yeah. Good point. The whole thing is A minus. And this one is A plus. Yeah. And that's why you will get rotation, right? Because if only sine, you just oscillate along here. Yeah. Good question. Yeah.
I was confused about the difference between a transmon and a squid. So can you go back to your diagram there? Yeah, so if I draw that 1x, that's a transmon, but if I draw 2x, this becomes a squid.
Actually, I'm not sure, but transmon usually is say that you have a Josephson junction with a large shunt capacitor. That is a transmon to reduce the charge noise, right? A squid is that you have 2 Josephson junction, right? So, but the goal of having 2 is because we want to use the flux to control the Josephson junction energy. So if we still treat it as a single Josephson junction and shunt it with a large capacitor, I think you still can call it transmon, right?
So I guess what Google and IBM do there using squid.
Actually, I don't know. I did not pay attention, but I
like you would imagine, because you need that knob to control the rest of the frequency. Putting many qubits.
probably yeah.
Because if you just had a